Okay, here's the second set of our video notes in our oceanography unit, this one being on tides and currents. To start off with, a little bit more about some of the properties of water. This one more specifically, we're going to be talking about the density of water. And so, as you probably remember from the lab that we did, which temperature of water is more dense? That would be cold water is more dense than hot water. And we also looked at fresh versus salty water. Which one of those was more dense? That would be the salty water is more dense. So the dense water, of course, because it's more dense, which way is that going to go? That type of water always sinks. So if you have cold water mixing with warm water, which one's going to end up on the bottom? The cold water. Same thing for the fresh or salty. The salty water would end up on the bottom, the fresh water would move up towards the top. So where are there differences in density? Well, if we look at these maps over here, we have the sea surface salinity, so the saltiness of the water. And so you can see that the water is most salty kind of near the center. It's definitely more fresh up here, like in the northern hemisphere, really, really salty over here, like in the Mediterranean Sea, things like that. And then we also look at temperature. It's going to be much, much warmer in the center of the globe, in the equator, where it's really, really warm. So warm water's at the equator. It's really cold at the poles, so cold water. And then for salinity, the salinity is highest in the middle, and it's lower salinity at the poles, like I just said. And kind of interesting, the average salinity of the ocean is only 3.5%, which is kind of unique, I think, or interesting, I think, because like when you taste salt water, if you're in the ocean, it tastes really, really salty. Really weird. So where would you expect to see the most dense water? Well, the water here is saltiest here in the center, which is more dense than this water up here. But whenever we go by temperature, warm water is less dense. So they're kind of unequal forces. But it turns out the temperature has more of an impact on density of the water. So why is this important? Why do we care about density? Because the density of water is what drives pretty much all of the currents in the ocean. We call it the thermohaline circulation. Thermohaline. Thermo means temperature. Haline means like salinity, basically. So driven by temperature and saltiness. And you can see over here on this map, you got different colored arrows. You have blue arrows that represent cold water. See, cold currents. Warm arrows represent warm water. And warm water moves towards the poles. So you can see here we've got a red arrow going north, a red arrow is going north, red arrow is going south in the southern hemisphere. And as it does that, it's obviously going to start to get colder because it's moving in a colder climate, and then as it gets colder, it starts to sink. And then once it goes to the bottom, it kind of stays down there for a long time. And it can travel all around the globe as these cold currents. Right? That's what the dark lines are. These are cold underwater currents. And then eventually it's going to come back up where it's going to get warmed and it's going to repeat. Right? We call this kind of like the global conveyor belt. You see that in this cartoon-ish drawing here. The warm surface currents go up, and then they cool and they go down, and then they come back up, or they come back up. And it's like a big conveyor belt, like what delivers your groceries to the cashier over at Safeway. And kind of an interesting thing is global climate change could stop this whole system. Right? We talk about global climate change, and maybe what's one of the biggest things you think of when you talk about global climate change is the melting of the polar ice caps. So imagine you've got all this water, or all this ice down here in Antarctica, or all this ice you can't really see up here at the North Pole or Greenland, and the ice is all fresh water. And so when that melts, that's going to dump a whole bunch of fresh water into the globe right here and right here. And fresh water being less dense, it's not going to sink. Well, where does the water usually sink? Hey, right up here, water sinking. And so if it can't sink there, it's like cutting that conveyor belt. We're going up, but instead of sinking and going on its way, it just stops. And so this whole climate change could stop, which would be really, really bad because, like we talked about, water controls or helps modify the climate. So if those things all stopped, the climate would be screwed, kind of like the movie Day After Tomorrow, if you guys have seen that before. So when you're looking at the map of the currents in that last slide, you might have noticed that a lot of the currents were moving in rough circles. Like, for example, here in the Atlantic Ocean, they're moving in a clockwise direction. In our Pacific Ocean, clockwise direction. Here we are over here, moving in a clockwise direction. Then when you're in the southern hemisphere, moving in circles as well, but now they're going counterclockwise. All right. These system of rotating currents are called gyres, G-Y-R-E-S. Gyres is how you say it. And why do they always rotate in circles, and how come they go opposite each other? Well, they're caused by a couple different things. Obviously, wind plays a big role in moving water. Bathymetry is the sea surface features, or the sea floor features. So, like, for example, here, we're tending to move in a circular fashion because this is where the water's moving. Down here, you can see this is kind of like where the bowl is at the basin, so it's moving that way. But also it's driven a lot by the Coriolis effect. This is kind of these mystical forces where anything that's moving in the northern hemisphere kind of gets deflected to the right, and if it's in the southern hemisphere, it's going to get deflected to the left. So, for example, when you flush your toilet, if left to its own devices, the water will go around that way. If you're in the southern hemisphere, it'll go the other way. And like snipers actually take this into account. If they're doing a really, really long shot, they would have to aim to the left a little bit in the northern hemisphere because of the way the Earth is turning. That bullet is going to curve slightly to the right, and that same effect plays into the role with the currents too. So by and large, the currents are going to go clockwise in the northern hemisphere and counterclockwise in the southern hemisphere, and those are called gyres. Another type of ocean currents, or a movement of water, is called upwelling. So upwelling being the warming and the rising of the cold, deep currents. So this is sort of the other half of what I was talking about a couple slides ago. Water sinks, but it has to come back up. Well, as it's been cruising around in the bottom of the ocean, it's been picking up nutrients from all the stuff that dies and sinks down there and decomposes, kind of like fertilizer, and that comes up and it brings that nutrient-rich water with it. And so wherever that water comes up, it's like a place where there's lots and lots of fertilizer. So that's going to be providing nutrients. So if you look over here, nutrients, that's going to be feeding the algae, and the algae is going to be feeding the little guys that eat the algae, and those little guys feed the bigger fish, and they feed the bigger fish. So wherever you have upwelling, this is where you have, it's like basically a lawn that's getting a lot of fertilizer, so there's a lot of grass there, and that kind of feeds the whole food chain, and everybody does really, really well. And you kind of see this happening a little bit with this graph here, looking at temperature as well as the amount of chlorophyll that you see. So pigment, you see down here, that's the amount of chlorophyll, and there's lots and lots and lots of chlorophyll right here along the coast. And if you look at the same area, but temperature, this is really, really cold water. So you've got cold water coming up from underneath, with it's bringing lots of fertilizer, which is feeding all those phytoplankton or algae, and that's helping everything else in the food chain. In addition to upwelling, animals use those currents because they can kind of hitch a ride on them, kind of like hitching a ride on the EAC and Finding Nemo. Tuna do the same thing. You know, remember, you've got currents moving all through this area here, and then the tuna are doing the same thing. They're using those currents to figure out wherever they need to go. See areas where they're fishing for tuna, roughly showing up at the same spot where all these currents are. So tuna know to use the currents. They're not stupid. And then finally, the last bit of water movement we're going to talk about are the tides. Right? High and low tide, you guys have probably seen this, the water coming in and out on the beach. And basically, tides are controlled mostly by the moon, but a little bit of the sun's gravity. And there's a couple different types of tide that we talk about. The spring tide is when the moon and the sun are in line, and this is where you get the greatest tide. So you have the highest high tide, but then on the other end of the spectrum, you have the lowest low tide. So here we over here, spring tide, and you can see this is any time where the Earth and the moon and the sun are all in line, and so the moon and the sun's gravity are both pulling on the water. You can see you have a really, really big bulge in this bit of water, and so that's kind of representing the tide. You have the highest tide. And the opposite of that is called a neap tide, where the sun and the moon are at right angles, and this is where we have the least difference of tide. So you would have the lowest high tide, right, because it wouldn't come up as far on the beach. And you can see because you've got gravity pulling this way, but you also have gravity pulling this way, and so the bulge, you can see that bulge of water is not as big during a neap tide as it is during the spring tide. I would highly recommend that you draw a little sketch in your notes somewhere off the side that shows the sun, the moon, and the Earth and being spring tide versus a neap tide. I think that would be pretty helpful for you. just because it's kind of cool if you're ever on Jeopardy. The place in the world that has the greatest tides is the Bay of Fundy. So this is in Canada, kind of a little bit north of Maine, over near where I'm from. You got some pictures here where this is high tide, and then low tide, where this is basically all exposed land. You can see over here high tide, low tide, no water at all. And this is where they have the greatest tides. It's actually, in a way, kind of tragic because a lot of people die because probably mostly tourists. They're out here and like, oh my God, look at this. The tide's gone. We can walk out so far, and they're out here. And then all of a sudden the tides come flooding back in, and a lot of people get caught out here in no man's land every year and die, which is kind of sad. But still, Bay of Fundy, just a little neat little trivia fact. I'm not going to ask you that in the test or anything like that. So that is the end of the notes for our oceanography section. Don't forget to do the quiz.